Hello and welcome back to the Sleepy Geographer. Tonight, we're taking a gentle journey beneath our feet, exploring the hidden world that has been quietly shaping our planet for billions of years. Before we begin, let me know in the comments where you're listening from and what time it is where you are. I always enjoy seeing people from all around the world joining these peaceful journeys. Now, get comfortable, settle in, and let's begin. Right now, wherever you are, there is ground beneath you. Maybe it's a few floors of building between you and it. Maybe it's just a mattress, a floor, a slab of concrete, and then the earth itself. But it's there, and it goes down much further than most people ever consider. Down past the part that gets rained on. Down past the part that holds up trees. Down into rock that has been sitting in the dark for stretches of time so long that human history, all of it, from the very first fire to right now, would barely register as a passing moment against it. We're going to start close, just beneath your feet, where the world is thin and solid and familiar. And then we're going to keep going, level by level, until we reach something that most people never learn exists at all. A place far below anything we would call underground in the ordinary sense, where scientists believe there is more water locked inside solid rock than in every ocean on the surface combined. But that's much later. For now, just the crust, just the first layer, the one everything else stands on. Picture, for a moment, an apple sitting on a table. Not because the earth looks like an apple, but because of the proportions. If the whole planet were shrunk down to the size of that apple, the skin of the apple, the thin part you'd peel away with a knife, would be thicker than the crust of the earth relative to everything below it. That's how shallow the ground under your feet actually is, compared to what the planet holds beneath it. We live our entire lives on something closer to a skin than a floor. The crust is not the same everywhere. Under the oceans, it is thin and dark and young, made mostly of a dense volcanic rock called basalt, constantly being created at cracks in the ocean floor and constantly being pulled back down elsewhere, recycled every so often on a geological clock that makes it, on average, far younger than the crust under the continents. Under the continents, the crust is thicker, lighter, and in places extraordinarily old. Rock that has been sitting quietly in certain regions of Canada, Australia, and southern Africa for stretches of time that stretch back further than almost anything else on the surface of this planet. Human beings have tried, a few times, to see how far down through this crust they could actually reach. On the Kola Peninsula in the far north of Russia, engineers spent nearly 2 decades drilling a single borehole straight down into the continental crust, hoping to reach as deep as technology would allow. They made it further than anyone before them, deep enough that if you dropped a stone into the opening, it would take a long moment of silence before you heard anything at all. And yet, measured against the whole thickness of the crust beneath that spot, they had barely broken through the surface. The drill bit finally stopped, not because it ran out of rock to pass through, but because the rock itself had grown too hot, too soft, too willing to bend rather than fracture for the equipment to continue. That's the strange thing about heading down through solid ground. It doesn't stay cold and hard forever. Somewhere in that descent, temperature starts to change. Not much, not at first, but steadily. For every kilometre you go down, on average, the rock gets a little warmer. Not because of the sun. The sun's warmth barely reaches a few meters into open ground before it disappears entirely. This warmth comes from below, from heat still leaking out of the planet's interior, heat left over from its formation, and heat still being generated deep inside by the slow decay of radioactive elements in the rock itself. The ground is warm, not because of anything happening above it, but because of something happening far beneath it, something that has been going on since before there was a surface at all. Down here, in the upper crust, is where nearly everything geological that shapes daily human life actually happens. Earthquakes begin here, along fractures called faults, where two blocks of rock are pressed against each other and occasionally slip. Most of the time, a fault is simply resting. Two surfaces of rock, locked against each other by friction, holding perfectly still for years, decades, sometimes centuries, while pressure steadily builds on either side of them from the slow movement of the plates above. Nothing about a resting fault looks any different from the rock around it. It gives no outward sign of what it's holding back. And then, eventually, in a moment that might last only a few seconds, it slips, and everything that had been building in silence for however long is released all at once. Groundwater moves through here too, filling cracks and pores in the stone, seeping downward at a pace so gradual it can take decades for a single drop of rain to travel from the surface to wherever it eventually settles. Oil and gas sit trapped here as well, in rock formations that acted like slow filters over long periods, letting some things pass through and holding others back. And it is here, too, in this upper stretch of crust, that soil begins. Soil feels like something separate from rock, something soft where rock is hard, something alive where rock is still. But soil is rock's own slow transformation. Every handful of dirt anywhere on Earth started out, at some point, as solid stone. Picture a bare rock face somewhere on a hillside. Rain lands on it, day after day, season after season. Some of that water finds its way into the tiniest cracks in the surface. At night, in a cold season, that water freezes, and as it freezes, it expands, pressing outward against the stone around it with a quiet but relentless force. The crack widens. A little more water gets in the next time. The cycle repeats, over and over, for a length of time that would make a human patience seem laughably short by comparison. Eventually, a piece breaks free. Then another. The solid rock face becomes, grain by grain, something looser, something that can hold water and air between its particles instead of just resisting them. Wind carries some of that broken rock away and deposits it somewhere else. Rivers carry more of it, grinding it smaller as they go, rounding its edges, sorting it by size the way water always does. The heaviest particles settling first, the lightest ones drifting furthest. Lichens, those quiet partnerships of fungus and algae that can live on almost bare stone, settle onto what remains and begin to break it down chemically, releasing faint acids that dissolve minerals molecule by molecule. When the lichens eventually die, they leave behind a thin trace of organic material, and that trace becomes the very first ingredient of something that isn't purely rock anymore. This is where soil begins. Not as dirt falling from somewhere, but as stone slowly giving up its solidity, mixed with the remains of whatever manages to grow or crawl or root itself into that first loosening structure. If you dig down through healthy soil almost anywhere, you'll pass through recognizable stages, though the details shift from place to place. Near the top is a dark, crumbly layer, rich with the decayed remains of leaves, insects, and everything else that has ever lived and died on that particular patch of ground. This is the layer most gardeners think of when they picture soil, and it is astonishingly alive. A single handful of healthy topsoil can hold more individual living organisms than there are people on Earth. Bacteria too small to see, fungal threads stretching for meters if unrolled, insects, worms, mites, and countless other creatures whose entire world is contained within a space you could hold in one hand. Now consider that same handful of soil at night, in a quiet forest, magnified far beyond what any eye could actually manage. A beetle grub moving through a tunnel it dug the previous week. A thread of fungus extending its tip forward by some impossibly small distance, searching for a trace of moisture. A single earthworm easing its way through a channel already softened by the worm that passed through days before. None of it makes a sound a human ear could register. None of it happens quickly enough to catch with a glance. and yet all of it is constant. Every hour, every night, in soil beneath forests and fields and quiet backyards everywhere on Earth, whether anyone is there to consider it or not. Below that dark, living layer, the soil pales and thins. Fewer roots reach this deep. Less organic material has had the chance to accumulate. This is the layer where minerals leached from above tend to settle, carried down by rainwater passing through the layers above and depositing what it carries once gravity and chemistry decide the journey is finished. And below that, finally, is the layer where soil gives way back to broken rock. Fragments too large to be called soil, too weathered to be called solid stone. The transition zone between the living world above and the far older world below. The whole system works like a slow conversation between the surface and the depths. Rock breaks down and becomes soil. Soil supports roots, insects, fungi, and the endless cycle of things growing and dying and being absorbed back into the ground. And underneath all of that quiet activity, more rock waits, patient, unweathered, exactly as it has been for longer than anyone could easily measure, until its turn eventually comes to be broken down as well. There is a particular kind of stillness to standing in a forest and knowing this is happening under your feet at every moment, in complete silence, without asking for any attention at all. The soil does not need you to notice it working. It simply continues the way it always has, turning stone into something that can hold water, hold roots, hold entire ecosystems that never once think about the ground that makes their existence possible. And speaking of roots, because soil on its own is only half the underground story of a forest, there is another layer worth sinking into before we go any deeper. A layer made not of stone or mineral, but of living wood, reaching down into the dark in search of water and something else it did not expect to find there. Beneath any healthy forest, hidden completely from view, lies a second forest. Not one made of trunks and branches rising into daylight, but one made of roots reaching downward and outward into darkness, tangled together so completely that in many places it becomes almost impossible to say where one tree's root system ends and its neighbour's begins. A single mature tree might have a root system stretching 2 or 3 times wider than its visible branches above ground. Thick structural roots anchor it against wind and gravity, plunging down and outward from the base of the trunk. But most of a tree's root mass isn't made of these thick anchoring roots at all. It's made of something far finer, tiny root hairs, some no wider than a human hair itself, spreading through the soil in a network so fine and so extensive that the total length of root hairs beneath a single large tree, if somehow untangled and laid end to end, could stretch for many kilometers. These fine roots are searching, constantly, for water and for dissolved minerals the tree cannot produce on its own. But they are not searching alone. Wrapped around and through nearly every one of these root tips is something that does not belong to the tree at all. A separate organism, a fungus, whose own microscopic threads extend the reach of the root far beyond what the tree could manage by itself. This partnership between root and fungus has a name, mycorrhizae, though the name matters far less than what it actually does. The fungal threads, thinner than the tree's finest roots, spread through soil the tree's own roots could never reach, drawing in water and minerals like phosphorus that would otherwise remain locked in the ground. In exchange, the tree, which produces its own food through sunlight and cannot get that from soil no matter how far its roots spread, passes some of that sugar down through its trunk, down through its roots, and out into the fungal network wrapped around them. It is a trade struck in complete darkness, underground, between 2 entirely different kinds of life, and it has been happening for longer than trees themselves have existed in anything resembling their current form. In certain old forests along the Pacific coast of North America, researchers have spent years mapping exactly which trees are connected to which, tracing fungal threads the way you might trace wires behind a wall. What they found were older, larger trees standing at the center of dense webs of connection, linked through the soil to dozens of younger trees around them. Some researchers have taken to calling these older trees hub trees, standing at the middle of a network the way a single old lamppost might stand at the center of a dozen streets branching outward from it in the dark. Cut down a hub tree, and the seedlings connected to it through the fungal network often struggle in ways that seedlings near younger, less connected trees do not. A kind of underground absence that shows up weeks or months later in the slower growth of trees that never touched the one that fell. But what makes this underground world truly strange is what happens once you realize this fungal network does not stop at any single tree. The same strand of fungal thread that wraps around the roots of one tree often continues on, unbroken, to wrap around the roots of another tree nearby. And that tree connects to another, and that one to another still, until an entire forest floor can be linked together by a single, continuous, living web spreading through the soil in every direction. Scientists studying old-growth forests have found that carbon, water, and even chemical warning signals can pass from tree to tree through these fungal connections. A young sapling struggling in deep shade, unable to produce enough of its own sugar through its thin scattering of leaves, has been shown in some forests to receive extra carbon through this underground network, sent, in effect, from older, taller trees with far greater access to sunlight above. Whether this counts as generosity in any sense we would recognize is a question better left to philosophers than geographers. What matters, for our purposes tonight, is simply that it happens. Quietly. Underground. Completely invisible from above, where all anyone standing in that forest can see is trunks and shade, and maybe a bird moving somewhere in the canopy. There is something worth sitting with in that image. A forest that looks, from above, like a collection of separate individual trees, each one competing for the same light, the same rainfall, the same patch of soil. And yet, underground, in the part no one ever sees, it may be closer to a single connected organism than a group of strangers. Roots touching roots, fungal threads carrying sugar from one trunk to another. An entire hidden economy of exchange running beneath every quiet forest floor on Earth in the dark, without any need for anyone above to notice or understand it. This underground web has its own kind of resilience, too. Where a fire or storm removes some of the oldest trees, the fungal network they were connected to often survives in the soil, ready to link into the roots of whatever grows next. In some forests, researchers have traced fungal networks that appear, based on their size and the age of the oldest trees still connected to them, to have persisted continuously for many hundreds of years, outlasting individual trees the way a river outlasts any single wave passing across its surface. The deeper roots go, in certain regions, they eventually meet something the fine root hairs cannot pass through. Dense stone again. Not the loose, weathered stone of the transition layer just below the soil, but real bedrock. Dense, unbroken, indifferent to the pressure of even the strongest root pushing against it. Trees have their limits here. A root can widen a crack already present in stone, the way frost widens a crack, applying gentle, continuous pressure until something eventually gives. But a root cannot dissolve rock outright, cannot carve its way through unbroken stone the way water can, given enough time. And water, given enough time, can do things to rock that seem almost impossible to believe once you understand the numbers involved. This is where the story starts to change character. We've been moving, so far, through layers that are alive, or were recently alive, or are actively shaped by living things pressing against them from above. Soil, roots, fungal threads. But just beneath the deepest roots, in certain parts of the world, water has been quietly performing an entirely different kind of transformation for an extraordinarily long time. One that doesn't involve life at all, at least not directly, but instead involves a very particular kind of rock, a very particular kind of chemistry, and a patience that makes even the growth of tree roots look almost hurried by comparison. Limestone is not like most rock. Most stone, once formed, resists water almost completely. Granite, for instance, can sit exposed to rain for extraordinarily long stretches of time and barely change at all, at least not quickly enough for any living creature to notice. But limestone, formed from the same compressed remains of ancient sea creatures we might picture piling up on some long-vanished ocean floor, has a particular chemical vulnerability that most other rock simply doesn't share. It dissolves, slowly and only under the right conditions, but it genuinely dissolves, the way sugar dissolves in water, just at a pace measured not in seconds but in centuries. Rainwater on its own is not especially good at dissolving limestone, but rainwater is rarely on its own by the time it reaches the ground. As it falls through the air, and especially as it passes through soil thick with decaying plant matter, it picks up small amounts of carbon dioxide, and that carbon dioxide reacts with the water to form a weak acid. Nothing dramatic, nothing that would harm your skin if you touched it, but just acidic enough, given enough time and enough repetition, to very gradually eat away at limestone wherever the two meet. Picture that water reaching a crack in a limestone hillside, a crack so thin you'd need to look closely to even notice it. The slightly acidic water seeps into that crack and, molecule by molecule, dissolves a fraction of the stone along its edges. Then more water follows the same path, because it naturally follows the channels carved by earlier flows. The crack widens, almost imperceptibly. As the years became decades, and the decades became centuries, the crack that started as a hairline becomes wide enough for a trickle. The trickle becomes a thin stream, working its way down into the rock below, invisible from above, following gravity and the natural weaknesses of the stone toward whatever lies below. Landscapes shaped by this kind of slow limestone dissolving have their own name, karst, and they look distinct from almost anywhere else on Earth once you know what to look for. Hillsides pocked with sinkholes, streams that flow along the surface for a while and then simply vanish into the ground, swallowed by an opening in the rock, continuing their journey somewhere below where no one above can follow them with their eyes. Valleys with no rivers in them at all, because the rivers that once carved those valleys have long since found paths underground and abandoned the surface entirely. Consider standing at the edge of one of these vanishing streams on a quiet afternoon. The water arrives from somewhere upstream, moving calmly between grassy banks the way any small stream might. And then, without any drama, without any change in its sound or its pace, it simply reaches a low opening in the rock and disappears into it. No pool, no hesitation, just water, choosing to continue its journey somewhere you can no longer follow, leaving the stream below that point dry and quiet, filled only with smooth stones that haven't felt moving water in longer than anyone nearby could tell you. Beneath a karst landscape, the process that began as a single widening crack eventually produces something far larger. As water continues finding its way down through the limestone, following every weakness, every joint, every subtle fracture in the stone, it begins to carve out open space. Not just narrow channels, but genuine rooms, chambers, corridors, entire systems of connected voids inside what was, not so long ago in geological terms, completely solid rock. This is how a cave begins. Not with a single dramatic event, but with water, choosing the path of least resistance over and over again for a length of time long enough that entire mountain ranges have risen and eroded away elsewhere on the planet while a single cave system continued its patient work below the surface. Some of the largest cave systems on Earth took shape over spans of time reaching back tens of millions of years. the water inside them still working today exactly as it worked when the first passage was nothing more than a crack too narrow to fit a hand through. Down there, right now, in caves scattered across every continent except the very coldest, water is still dissolving stone, still widening passages by fractions too small to measure in any single visit, still continuing a project that will not be finished by the time anyone reading this, or their children, or their children's children, has lived and died. And once that hollow space exists, once water has carved out a chamber large enough to stand in, walk through, or simply float a small boat across a hidden underground lake, an entirely different world opens up inside it. A world with its own air, its own temperature, its own peculiar sense of time, sealed away from the surface by nothing more than the surrounding stone the water spent so long dissolving in the first place. That's where we'll go next. For now, just notice the shape of what we've covered so far. Thin crust, holding up everything we know. Soil, forming slowly from that crust breaking down, alive with more creatures than most of us will ever consider. Roots, reaching into that soil and connecting entire forests underground through fungal threads no thicker than hair. And below all of it, in certain quiet corners of the world, water finding its way into limestone and beginning, drop by drop, to hollow out spaces that will eventually become some of the strangest and most silent places on the surface of this planet, even though, technically, they lie beneath it. The ground has been doing this the entire time you've been lying here listening. It will keep doing it after this video ends, after you fall asleep, after tomorrow arrives and the sun rises over whatever patch of ground you happen to be standing on. Somewhere right now, a single drop of slightly acidic rainwater is easing its way through a crack in limestone too narrow to see, continuing a journey that began long before either of us arrived to notice it. That drop of water we followed to the edge of the rock has already found its way through, and past it, and further down, joining countless others exactly like it in a passage that widened one grain of dissolved stone at a time into something large enough now to hold it his own air, sealed off from the surface, resting inside a chamber of solid limestone the way water rests inside a cup. Step into that chamber, in your mind, and the first thing you would likely notice has nothing to do with sight at all. It's the air itself. The moment you cross from the entrance passage into the deeper cave, the air changes in a way your skin registers before your eyes do. Cooler in summer, warmer in winter, steady in a way that outdoor air never quite manages to be. This steadiness comes from something simple. A few meters below ground, the daily and seasonal swings of surface temperature stop reaching. The rock above acts as insulation thick enough to smooth out the difference between a July afternoon and a January morning until, deep enough inside a cave, the temperature settles at roughly the average yearly temperature of the region above it and stays there month after month, almost without variation. A cave in a place with cold winters and hot summers becomes, underground, a place with neither. Just one temperature, remaining almost unchanged, regardless of what the sky above happens to be doing on any given day. There is a particular sensation to standing inside that stillness. Outside, temperature is something you're constantly negotiating with. A jacket you put on or take off, a window you open or close. Inside a deep cave, none of that negotiation exists. The air simply is what it is, and next week, next year, it will feel almost exactly the same, likely for longer than anyone standing there will be alive to check. People who work underground for long stretches, surveyors, biologists, the occasional caretaker of a show cave open to visitors, describe a peculiar adjustment that happens after enough time spent below. The body stops expecting change. Where a person on the surface glances instinctively at the sky each morning to gauge the day ahead, someone who has spent long hours in a single unchanging chamber loses that reflects almost entirely. There is nothing to check. The cave was one temperature when they arrived, and it will remain that same temperature when they leave. And somewhere in that certainty, a kind of mental quiet settles in that surface life rarely allows. Humidity behaves the same way, though for a different reason. Water is nearly always present somewhere close by in a cave, seeping through the rock, pooling in low corners, dripping from the ceiling. And that water slowly saturates the air around it until the cave holds close to as much moisture as it possibly can without actually condensing into fog. Walk into most deep cave systems and the air will feel damp against your skin almost immediately. A dampness that never quite reaches the point of being wet, but never fully goes away either. Airflow, or the lack of it, is its own quiet phenomenon. Some cave passages carry a faint, continuous breath of air moving from one entrance toward another, driven by tiny differences in temperature and pressure between the cave and the surface. Air is drawn in through one opening as the cave breathes out through a distant one, sometimes kilometers away, following a path no person could easily trace by sight alone. Cavers sometimes describe following one of these drafts through total darkness, letting the faint movement of air against their face guide them toward an opening they cannot yet see, the cave itself seeming to exhale a direction to follow. This breathing can shift with the seasons above, even though nothing about the temperature deep inside the cave itself ever changes. In winter, when surface air is colder and denser than the air resting inside the cave, that outside air can sink into lower entrances and push the cave's own warmer air up and out through higher openings, creating a slow, continuous exhale that can sometimes be felt as a faint warm breath rising from a crack in the ground on an otherwise freezing morning. In summer, the flow can reverse entirely, the cave now drawing air inward instead of releasing it, exhaling in winter and inhaling in summer on a cycle so slow and so quiet that almost no one standing at the surface ever notices it happening at all. Other passages hold air that doesn't move at all. Dead air, sitting in the lowest, most enclosed chambers, undisturbed for so long that its very chemistry can shift. Carbon dioxide, produced slowly by decaying organic material carried in from outside or seeping up from deeper in the rock, can accumulate in these pockets far beyond the concentration found anywhere at the surface. It happens with no drama at all, no smell, no visible change, nothing a person would notice until they'd already been breathing it for longer than is safe. Experienced cavers know to watch a candle flame or check equipment before entering the lowest chambers of unfamiliar systems, because air that looks and feels completely ordinary can, in these enclosed pockets, hold barely enough oxygen to sustain a flame, let alone a person moving through it unaware. It's a strange thing to consider, that the very calm that makes a cave feel so peaceful, so insulated from the noise and change of the world above, is the same stillness that can let its air quietly become something else entirely, with nothing on the surface ever giving a hint that it's happening. Sound inside a cave behaves unlike sound almost anywhere else a person is likely to stand. Above ground, even in the quietest countryside, there is nearly always something distant moving air. Wind through leaves, an insect somewhere nearby, traffic so far off it registers only as a low hum beneath everything else. Underground, past a certain depth, all of that disappears completely. What's left is a silence so complete that people who spend time in deep caves often describe becoming acutely aware of their own heartbeat, their own breathing, sounds the body produces constantly, but that the noise of ordinary life normally covers over without our ever noticing. Into that silence, water still drips. A single drop, falling from a point on the ceiling, landing somewhere below with a small, clean sound that seems far louder than it has any right to be, simply because there is nothing else in the entire chamber competing with it. Wait, and another drop will fall from the same point, roughly the same interval later, and then another, keeping a rhythm that has likely continued, essentially unchanged, for longer than any calendar has existed to measure it. Follow that drip down to where it lands, and you'll find where the next chapter of this underground story is quietly taking shape. A shape built not from dissolving rock this time, but from rock being rebuilt, mineral by mineral, one tiny deposit at a time, over a length of time that makes even the slow carving of the cave itself seem almost hurried by comparison. The water dripping from that ceiling isn't just water anymore. On its way down through the limestone above, it dissolved a small amount of the very stone it passed through, carrying tiny amounts of calcium in solution, invisible, weightless, present only as a faint chemical trace within each drop. When that drop finally reaches the open air of the cave chamber, something changes. The carbon dioxide that helped dissolve the limestone in the first place begins, very slowly, to escape from the water back into the cave air, the same way carbon dioxide escapes from a glass of sparkling water left open on a table. As it escapes, the water becomes less able to hold the calcium dissolved within it. A tiny, nearly invisible trace of that calcium comes back out of solution and is left behind, deposited as a thin mineral ring exactly where the drop clung to the ceiling before falling. One drop leaves behind essentially nothing. You could stand and watch 1,000 drops fall from the same point and never see any difference at all in the rock around it. But caves do not work on the timescale of a single evening's patience. They work on a timescale where 1,000 drops is nothing, where 1,000,000 drops is barely a beginning, where the true unit of measurement is not the drop at all, but the century. Over centuries, drop after drop, leaving behind its faint trace of calcium in the exact same spot, a shape begins to grow downward from the ceiling. It starts as something barely thicker than a strand of thread, hollow at its center, water still traveling down through the middle of it exactly the way it always has. This hollow, narrow beginning eventually thickens, one mineral layer at a time, year by year, into the familiar tapering icicle shape most people picture when they think of a cave. A stalactite hanging from the ceiling, pointed downward, growing not in sudden bursts, but in additions so small that a formation you could see slowly lengthening, if you had the patience of centuries to watch it, would still be measured at the very fastest, in a matter of a few centimeters added across an entire human lifetime. Below it, where each drop finally lands on the cave floor after completing its long fall from the ceiling, the same basic process happens again, in reverse. The impact of the drop and the slight additional escape of carbon dioxide that happens when it splashes causes another small deposit of calcium to be left behind. Not hanging from above this time, but building upward from below. A stalagmite, rounder and thicker than the stalactite forming above it, growing toward the ceiling the same patient way its counterpart grows downward to meet it. Given enough time, and cave systems have access to more time than almost anything else on the surface of this planet. A stalactite reaching down and a stalagmite reaching up will eventually touch. Where they meet, the two formations fuse into a single continuous column of stone, floor to ceiling, solid, permanent, a structure built entirely by water and patience with no other tool involved at all. Some of the columns found in the largest cave systems in the world took so long to complete that their growth began before the first cities existed anywhere on the surface above them, and they were still growing, drop by drop, when those first cities eventually rose and grew, and in some cases fell into ruin, all while the column beneath the ground continued its work exactly as it always had, indifferent to anything happening so far above it. Not every formation in a cave hangs straight down or stands straight up. where water seeps through the rock more broadly rather than gathering into a single dripping point. It can spread thin, mineral-laden sheets across walls and sloped surfaces, building up in delicate folds that genuinely do resemble draped fabric, thin enough in places that light shown from directly behind can pass faintly through the stone itself. Elsewhere, mineral-rich water flowing gently over a rounded surface builds smooth, rippled coatings that catch whatever light touches them and hold it in soft curves, like something poured rather than grown. And in certain rare, specific conditions, where water seeps from the wall itself rather than dripping from above, moving so slowly that gravity has barely any say in the matter, thin, curling growths can form that seem to defy the pull of gravity almost entirely, twisting outward from the rock in directions that have less to do with straight lines and more to do with the precise, invisible currents of air moving through that particular corner of the cave. These formations are rare enough and delicate enough that many of the world's most protected cave chambers exist specifically to keep them from ever being touched by a careless hand, because a formation representing tens of thousands of years of drop-by-drop patience can be broken in less than a second by someone who never meant any harm at all. Stand in a chamber filled with these formations, lit only by whatever light you've carried in with you, and the shapes around you can start to feel almost deliberate, as if something had been sculpting with real intention, real design, choosing exactly where each column should stand and exactly how each curtain of stone should fold. But nothing here was designed. Every shape is simply the visible record of water following the only rules it has ever followed. Dissolve what you can, carry what you dissolve, release it again when conditions allow, and repeat that pattern for so long that the accumulated result eventually looks, to a temporary visitor from the surface, like something built with purpose. There's a particular kind of vertigo that comes from truly grasping how long some of this took. A formation as thick as your arm might represent something in the range of 10,000 years of dripping, drop after drop, night after night, through every kind of surface weather imaginable happening far overhead, through ice ages, through the rise and fall of entire civilizations, through every war and every peace treaty and every single day any human being has ever lived. While underground, in complete darkness, nothing about the process ever sped up or slowed down or paused to notice any of it. Even the color of these formations tells a kind of story if you know how to read it. Pure calcium carbonate, deposited slowly and evenly, tends toward white or pale cream, almost translucent in thin sections where a light held behind it can shine faintly through. But water rarely carries only calcium. Traces of iron oxide staining the stone can turn a formation warm orange or rust red, evidence of a period when the water passing through carried a little more iron than usual, perhaps from a particular layer of rock it happened to pass through on its way down. Streaks of black or grey sometimes mark the presence of manganese, deposited in the same slow, patient way as the calcium around it, but leaving a very different mark behind. A single large formation can carry every one of these colours in banded layers, each band a quiet record of some subtle shift in the water feeding it, centuries or millennia apart, readable the same way rings inside a felled tree record each year of its life. Which brings us to something worth sitting with for a while. The particular way time behaves once you're far enough underground that the surface stops being able to reach you. On the surface, time announces itself constantly. The sun rises and sets, marking each day with unmistakable clarity. Seasons shift the color of leaves, the temperature of the air, the length of daylight hitting your face. Even without a clock or calendar, a person could roughly track the passage of weeks and months just by paying attention to what the sky and the ground around them were doing. None of that exists in a deep cave. No sunlight reaches far enough down to mark day from night. No seasonal shift in temperature occurs to hint at whether it's winter or summer somewhere far above. The air stays the same. The dark stays the same. Water still drips at its same slow interval, but that interval has nothing to do with the hour of the day or the month of the year. It simply continues at whatever pace the geology above happens to allow, regardless of what's happening to the sun. People who have spent extended periods in deep caves for research, often as part of experiments specifically designed to study how humans perceive time without any external cues, tend to report something remarkable. Their internal sense of a day's length gradually drifts away from 24 hours entirely. Removed from sunlight, removed from clocks, the human body left to its own devices tends to settle into a rhythm of sleeping and waking that stretches slightly longer than a surface day, sometimes by a significant margin, without the person having any conscious sense that anything unusual is happening. They simply feel, at the end of what their body considers one full day, that it's time to sleep again. Even if, on the surface, more than 24 hours has actually passed. Some of these researchers, once they finally return to the surface after weeks spent underground, describe a peculiar disorientation upon learning how much time has actually passed. Their own sense of the calendar, built entirely from an internal rhythm with nothing external to correct it, had quietly drifted its own course the whole time, adding up small differences day after day until the gap between felt time and actual time had grown into something noticeable, even startling. It's a gentle reminder that so much of what feels fixed and certain about time is, in fact, borrowed entirely from the sun and disappears almost immediately once the sun is no longer there to lend it. This isn't merely a curiosity about human biology. It says something deeper about what a day even means. A day is not some fundamental unit built into the universe. It's a consequence of a planet spinning while orbiting a star, visible and meaningful only to creatures standing on that planet's illuminated surface. Take away the sunlight, and the day, as a concept your body can feel, quietly begins to dissolve. Not painfully, not dramatically, just gradually, the way anything dissolves in the dark when nothing steps in to reinforce it. The cave itself, of course, has no need for days at all, and never did. It measures time, if it measures anything, only through the accumulation of mineral in a column, the slow retreat of a wall dissolving fraction by fraction, the barely perceptible widening of a passage that started once as a crack too narrow to notice. These are not measurements marked in hours or days or even years in any way the cave itself would recognize. They are simply the shape the rock has slowly become in response to whatever has been happening to it for however long it's been happening. There is something quietly comforting in that if you let yourself sit with it. Somewhere below the ground right now, in complete stillness, entirely unconcerned with whatever hour it happens to be, wherever you are, water continues dripping into the darkness exactly as it has for longer than anyone reading this could properly imagine. It isn't waiting for anything. It isn't keeping track of anything. It's simply continuing, the way stone and water continue everywhere on this planet, whether anyone above ever thinks to notice or not. Follow that dripping water further, past the chambers of hanging stone, and it eventually gathers into something larger than a single trickle finding its way from ceiling to floor. Deep inside many limestone systems, especially in regions where the rock sits low enough to intersect the water table, these countless small trickles combine into genuine underground rivers. Flowing water, moving with real current, carving its own path through stone in total darkness, the same way a surface river carves a valley beneath open sky. An underground river doesn't behave quite like its surface counterpart, though the basic physics remain the same. Water still seeks the lowest available path. It still moves faster where the passage narrows and slower where it widens into open chambers. It still carries sediment, grinding at the rock beneath it, widening its channel by degrees too small to notice on any single visit, but unmistakable when compared across centuries. What differs entirely is the absence of sky, of banks lined with plants, of any of the surface signals a river usually offers to mark its presence. An underground river simply appears out of solid rock at one point, flows through a passage barely wide enough in places for a single person to pass, and disappears again into another opening further along, continuing towards some resurgence point that might be a hidden spring, kilometers away, that no one standing beside it would ever think to connect back to the water flowing invisibly beneath their feet. Cave divers who have mapped these systems describe a particular quality to the water in the deepest, most enclosed underground rivers. A stillness and clarity that surface water almost never achieves, precisely because it has never been disturbed by wind, by rain falling directly onto it, by anything at all beyond the occasional passage of a fish or crustacean that has adapted over countless generations to a life spent entirely without light. Visibility in some of these underground channels stretches for tens of meters in every direction. The water so clear and so undisturbed that a diver's lamp seems to illuminate a held breath of space around them rather than water at all, as if they were floating through absolutely nothing, with stone walls simply happening to exist wherever the light chose to land. The creatures that live in these channels carry their own quiet testimony to how long these waters have been flowing undisturbed. Blind fish, pale and almost translucent, having lost the need for eyes across generation after generation spent somewhere pigment and sight served no purpose at all. Cave-adapted crustaceans, ghost white, moving through the dark by senses built entirely around touch and vibration rather than vision. None of them arrived here recently. Each one represents a lineage that found its way into this darkness a very long time ago and simply never left, slowly shedding whatever it no longer needed in a place where needing it would have made no difference at all. Where an underground river slows, in a chamber wide enough and deep enough for the current to lose its urgency almost entirely, it settles into something closer to a lake than a river. A body of still, dark water resting inside stone, fed slowly from one direction and drained slowly from another, its surface so calm in the absence of wind that a single dropped pebble creates ripples that can be watched, crossing the entire width of the chamber, uninterrupted, before finally fading against the far wall. These underground lakes hold their own particular silence, distinct even from the silence of the dry chambers above them. Sound doesn't just fail to travel far in a cave, near still water. It also reflects, bouncing faintly off the surface and back off the ceiling, until a single dripped note from somewhere above seems to arrive from several directions at once, softened, doubled, uncertain of its own origin. Standing at the edge of one of these lakes, with a light lowered just enough to see the water without disturbing the silence completely, it's possible to notice something a little unsettling in the best possible way. The water is often so perfectly clear and so perfectly still that it becomes genuinely difficult to tell where the water ends and the reflection of the ceiling above it begins. Two caves, it can seem, one hanging with stone formations reaching down from above, and one hanging with the exact same formations reaching up from below, meeting at an invisible line that only reveals itself the moment something breaks the surface. Somewhere in one of these underground lakes, deep beneath the ground, in a chamber that has likely never once been touched by any light beyond whatever a rare visitor has carried in on their own, the water is resting right now exactly as it was resting 100 years ago, and exactly as it will likely be resting 100 years from now. Patient, dark, untroubled by anything happening on the surface, far above it, holding its stillness the way only something entirely removed from wind and weather and daylight ever really can. We'll follow that water further still, because in some places, this quiet underground world doesn't stay hidden forever. In certain regions, the ceiling above one of these chambers eventually grows too thin, too weakened by all the dissolving that built the chamber in the first place, and it simply gives way, collapsing downward all at once, after standing firm for longer than anyone could measure, and opening a sudden window from the surface directly down into water that has been waiting in darkness for longer than any calendar above it has existed. That's where we'll go next time we continue this journey, down through one of those openings, into water lit, for the first time in longer than it can remember, by daylight falling directly onto its surface from above. For now, let the stillness of that underground lake settle over you the way it settles over the chamber that holds it. No wind reaching it. No sound but the occasional drop, falling from somewhere in the dark, landing on a surface that has been waiting, without impatience, for exactly this. Somewhere above one of these hidden lakes, the ceiling has been thinning for longer than anyone standing on the surface would ever think to check. Water has been dissolving it from below for the same reason it dissolved everything else on this journey so far. Patient, chemical, indifferent to whatever is happening in the world above. And at some point, after the ceiling grows too thin to bear its own weight, it stops resisting gravity at all. It falls. Not gradually, the way most of this underground world changes. All at once. A section of rock that had been standing for thousands of years, sometimes tens of thousands, simply gives way in a single collapse, dropping into the water below and leaving, where solid ground used to be, an opening straight down from the surface into a chamber that has never once felt open air across its entire history. This is how a cenote begins. The word itself comes from the Yucatan Peninsula in Mexico, where thousands of these collapsed openings dot the landscape, each one a nearly perfect circular window down into water that had been sealed away in darkness until the moment the ceiling above it finally failed. Stand at the edge of one on a clear day and look down, and the first thing that strikes most people is the colour. Sunlight reaching water that has spent its entire existence in complete blackness produces a blue unlike almost anything found on the surface. A blue that seems to glow slightly from within the water itself, rather than simply reflecting the sky above it, because the water is so clear, so free of the sediment and algae that cloud most surface lakes, that light can travel unusually far into it before, scattering back up toward the eye. Around the rim, tree roots often hang down into the opening, some of them stretching many meters below the point where soil gives way to open air, reaching toward water their trunks, rooted high above in ordinary daylight and rain, would otherwise never reach. It is a strange sight, roots dangling in open space, suspended in the same shaft of light that only recently began reaching that particular patch of water for the first time in the water's entire existence. Birds are often the first to notice a cenote from above, long before any person stumbles across one in the forest. Swifts and swallows nest in the walls just below the rim, riding the column of cooler air rising out of the opening the way a hawk rides a thermal, circling down into the shaft and back up again in long, unhurried loops. Their calls, echoing off the curved stone walls, are often the only sound marking the presence of an opening that might otherwise be completely hidden beneath a canopy of trees, invisible from more than a few paces away until the ground simply stops and the blue appears. The temperature difference is immediate the moment you cross into the shaft of open air above a cenote. Standing at the rim, in full sun, the heat of the day presses down the way it does everywhere in that region. But the air rising up out of the opening itself carries the same coolness as the deep cave chambers we've already passed through, because that's exactly what a cenote is at its foundation. Not a lake that happened to form in a hole. A cave chamber, one that spent its entire history in total darkness, exactly like every other cave chamber in this story, that simply happened to have its roof fail at some point in the past, letting the surface world in through a single opening, while everything below that opening remains, in every other respect, still part of the underground. Descend into one by rope, or by a set of stairs cut for visitors, and the light behaves in a way that takes a moment to understand. Near the surface, everything glows. The water lit almost entirely from above, bright and blue and welcoming. But look toward the edges of the chamber, toward where the walls curve away from the opening and back under the overhanging rock that never collapsed, and the light gives way quickly to the unchanged absolute darkness found in any cave untouched by any opening at all. A cenote is not fully lit. It is a single shaft of daylight surrounded, on every side beneath the surface, by the familiar darkness it interrupted. Some cenotes stay open like this, a single clear pool beneath a hole in the canopy above, the water visible from the rim all the way down. Others connect, beneath the surface, to entire cave systems extending outward in every direction, the collapsed opening acting as nothing more than a single doorway into a network of flooded passages that a diver could follow for kilometers without ever seeing daylight again after leaving that first bright entrance behind. Along the coastline, where limestone meets the sea, the same basic process produces something slightly different. Openings that connect not to freshwater cave systems inland, but to the ocean itself, sometimes plunging to depths of well over 100 meters straight down through a nearly vertical shaft in the rock. These are usually called blue holes, and from above, on a boat looking down into water that would otherwise be a uniform shallow turquoise across a shallow reef, they appear as a sudden, startling patch of deep, almost black-blue water, marking exactly where the surrounding seafloor drops away into a shaft that was, at some point in the deep past, a dry cave chamber on dry land before rising seas, eventually flooded it from below. The most famous of these, off the coast of Belize, was first mapped in detail by a team travelling with the oceanographer Jacques Cousteau in the 1970s, who described looking down into it from the surface as looking into the pupil of a vast blue eye set into the pale reef around it. What his team found beneath that surface were not open water at all, but the same stone we've been following this whole journey. The collapsed remains of a dry cave, its stalactites still hanging from what was once its ceiling, now angled and submerged, telling the walls of the shaft that this had been open air once, long before the sea ever rose to claim it. Divers who have explored the deepest of these blue holes describe passing through distinct layers on the way down, each one different from the one above it in ways you can feel even without instruments. Near the surface, ordinary seawater, warm, slightly cloudy, mixed by wind and current the way any exposed ocean water is mixed. Deeper, the water grows noticeably colder, and in some blue holes, a layer of nearly stagnant water sits trapped partway down, low in oxygen, sometimes tinted faintly by hydrogen sulfide seeping up from decomposing material that has settled there over a very long time, undisturbed by the currents that keep the water above it circulating freely. Below that layer again, in some of these formations, the water clears once more, cold and still, resting exactly the way the water in a landlocked cenote rests, indifferent to the ocean pressing against the rock just meters away. It's a strange thing to consider, standing at the edge of either kind of opening. The same basic geological process, limestone dissolving slowly in slightly acidic water over an unhurried stretch of time, producing both a quiet freshwater window inland, ringed by dangling roots and birdsong, and a plunging vertical shaft out at sea, ringed by nothing but open water and the occasional curious fish, drifting past the opening to look in. Every cenote, every blue hole, is really just a place where this underground story briefly surfaces. Look down into one, and you're looking into a chamber shaped by familiar water over the same impossibly patient span of time as every dry limestone cave we've already passed through in this journey. It only differs from those chambers in one respect. Its roof happened to fail. And beneath both kinds of openings, whether inland or out at sea, the water itself is never entirely separate from the water moving through the rock all around it. It's part of something much larger, something that extends far beyond the boundaries of any single cave or lake or cenote. A body of water held not in an open chamber at all, but inside the rock itself, filling the countless tiny spaces between mineral grains the way water fills the space between grains of sand on a beach. This is where the story turns, silently, from caves towards something a little less visible, and in some ways even more important, to nearly everything living on the surface above. Picture, for a moment, a layer of rock that isn't solid the way granite is solid, but porous instead. Sandstone, for instance, made of countless individual grains of sand compressed together over a long period of time, each grain touching its neighbors but never quite fusing into something completely without gaps. Between those grains, tiny spaces remain, connected to each other throughout the entire layer of rock, forming a network of openings far too small to see individually but present, collectively, across an area that might stretch for hundreds of kilometers underground. Water enters this network the same way it has entered every hidden place we've visited so far, through rain falling on the surface, soaking down through soil, passing through the transition layer where rock crumbles into looser material, and eventually reaching a layer porous enough to accept it. Once inside, that water doesn't pool the way it would in an open cave chamber. It fills the spaces between grains directly, the way water fills the space between marbles packed into a jar, present everywhere throughout the rock rather than gathered into any single visible body. A layer of rock capable of holding and transmitting water this way is called an aquifer, and beneath the ground in nearly every part of the world, whether anyone above realizes it or not, aquifers exist in a great patchwork of overlapping and separate layers, some shallow enough to be reached by a simple hand-dug well, others so deep that reaching them requires drilling through hundreds of meters of rock that holds no water at all before finally breaking through into a layer that does. The water inside an aquifer moves, though far more slowly than water moves anywhere else in this story so far. Through an open cave passage, water might travel a considerable distance in a single day. Through the tiny connected pores of a sandstone aquifer, that same distance might take years, sometimes many decades, the water inching forward through gaps barely wider than the water molecules themselves, pushed along not by any strong current but simply by pressure, by gravity, by the patient tendency of water everywhere to move from where there's more of it toward where there's less. Sometimes that pressure does something visible without any pump or well at all. Where an aquifer is trapped between two layers of impermeable rock tilted at just the right angle, the water inside can be under enough natural pressure that, once a well reaches it, the water rises on its own, sometimes all the way to the surface, spilling out without needing to be lifted by anything but the weight of the rock above pressing down on the layer that holds it. These are called artesian wells, and standing beside one that has been flowing steadily for decades, watching water rise out of solid ground with no pump in sight, gives a small, quiet sense of just how much pressure can build inside rock that looks, from above, like nothing more than an ordinary field. Because of this slowness, water drawn from deep in an aquifer today may have entered the ground as rainfall a very long time ago. Sometimes centuries before, in the case of the deepest and most enclosed aquifers, water that fell as rain onto a landscape that looked nothing like it looks now, filtering down through rock at a pace of perhaps a few meters each year, only now emerging from a well somewhere, far from where it first soaked into the earth. There is something worth pausing on in that thought. A glass of water drawn from a very deep well might contain rain that fell before the person drinking it was born, sometimes well before their parents were born, held quietly inside solid rock for the entire span of time in between, moving in the dark at a pace slower than almost anything else that moves at all, waiting, without any awareness of waiting, for the moment it would finally reach a well, a spring, or a river willing to carry it back to the surface. Some aquifers sit close enough to the surface that water within them is replenished quickly, within a single rainy season, rising and falling with the rhythm of local weather, almost the way a shallow pond would. Others, sealed above and below by layers of impermeable rock that water cannot pass through easily, hold water that has been essentially isolated from the surface world for a very long time, filling slowly, draining slowly, responding to nothing happening above except across timescales far longer than any single human life could track from beginning to end. These deep, ancient aquifers are sometimes called fossil water, because in every meaningful sense, the water inside them is a relic of a much older climate. Rain that fell during a wetter period in a region's history, stored underground ever since, effectively finished accumulating because the surface conditions that once fed it no longer exist in quite the same way. Draw from one of these aquifers today, and you are not drawing from something actively being replaced by current rainfall. You are drawing down a reserve, slowly, the way you might slowly spend savings set aside a very long time ago by someone who is no longer able to add anything more to the account. Beneath certain deserts, this fossil water sits in enormous quantities, filling ancient aquifer systems that were filled during periods thousands of years in the past when the region above them received far more rainfall than it does today. Wells drilled into these aquifers can produce clean, usable water in the middle of landscapes that receive next to no rain at all in the present, drawing on a reserve set aside long before the desert above ever became a desert, water that fell during a different climate, remaining undisturbed through the entire transition, resting in the dark exactly the way everything in this story tends to wait, without any awareness of how long it's been waiting or how much longer it might continue. Beneath the central United States lies one such reserve, a layer of sand and gravel left behind by ice sheets that retreated many thousands of years ago, now supporting a large share of the region's farmland from water that fell as rain or snow during a much colder and wetter period in the land's history. Beneath the Sahara, in an even more striking example, lies a fossil aquifer holding water that soaked into the ground during a time when that desert was green and rained on regularly. Water old enough that some of it fell before the pyramids were built, resting quietly underground through every century of desert that followed. Elsewhere, aquifers replenish constantly, closely tied to the surface water cycle in a relationship worth following all the way through, because it explains where nearly all of this underground water ultimately comes from and, eventually, where it ultimately goes. Rain falls onto the ground somewhere on the surface. Some of that water runs off immediately, gathering into streams and rivers that carry it, quite visibly, toward lakes and oceans. But a portion of every rainfall doesn't run off at all. It sinks. It moves down through the soil, through the crumbled transition layer beneath the soil, and eventually reaches either the water table, the upper boundary of ground that is fully saturated with water, or a porous layer of rock capable of holding it as part of a proper aquifer. Once underground, that water doesn't remain where it entered. It continues moving, however slowly, following gravity and pressure exactly the way water always does, eventually finding its way to a place where the rock permits it to re-emerge at the surface. This might be a spring, water pushing up through an opening in the ground under natural pressure, sometimes with enough force to bubble visibly, sometimes so gently that the water simply seeps out through soft ground without any visible source at all. It might be the bed of a river, where a stream that looks, from above, like it's simply flowing along the surface is actually being fed continuously from below, groundwater seeping up through the riverbed itself and adding to the visible flow without any obvious sign that it's happening. It might be, on the coast, an underwater spring emerging directly into the sea, fresh water bubbling up through the ocean floor from an aquifer that extends out beneath the water, its presence sometimes detectable only by the change in temperature or salinity of the water immediately above it. This entire hidden loop, rain sinking down, travelling slowly through rock, eventually returning to the surface somewhere else entirely, sometimes kilometers from where it first disappeared into the ground, forms an underground half of the water cycle that rarely gets the attention given to clouds and rain and rivers, despite being every bit as essential to how water actually moves around this planet. A very large share of the water flowing in the world's rivers, even on a day with no rain falling anywhere nearby, is water that entered the ground somewhere upstream, days or months or years earlier, and has only just now finished its slow underground journey back toward daylight. Think, for a moment, about a spring rising from the base of a hillside, clear and cold, flowing steadily regardless of whether it rained yesterday or 2 weeks ago. That water has already completed an entire hidden chapter of its journey before anyone standing beside the spring ever sees a drop of it. It fell as rain somewhere higher up the same hill, at some point in the past that might be recent or might be considerable, soaked down through soil and rock, travelled through the dark at whatever pace the local geology allowed, and finally reached a point where the rock could no longer hold it, releasing it back into open air at the exact spot where you happen to be standing, cold and clean and utterly, unaware of how long or how far it has actually travelled to arrive there. There are springs in limestone country cold enough and steady enough in temperature that local trout gather near their outflow through every season, drawn to the one part of the river that never freezes and never warms, a small patch of underground constancy leaking quietly into a world of surface extremes. Aquifers, in this sense, act as an enormous natural reservoir, storing water underground during wet periods and slowly releasing it during dry ones, evening out, over the long run, the difference between a rainy season and a dry one in a way that surface water alone never could. Rivers respond to rainfall almost immediately, rising and falling within days. Aquifers respond over months, sometimes years, smoothing the variation into something far steadier, far more patient, in keeping with everything else this underground world seems to prefer. Follow this water deep enough into a particular kind of aquifer, sealed and isolated for an especially long stretch of time, and every so often, in a small number of remarkable places on Earth, the very slowness that defines an aquifer produces something else entirely. Not water still moving through open pores, but water that has, in certain extraordinary chambers, been given enough time and the right chemical conditions to leave behind mineral structures unlike almost anything else found underground. There exists, beneath a mine in northern Mexico, a single chamber that receives almost no visitors, sealed most of the year behind a pumping system that keeps it from flooding, because the chamber itself sits below the local water table in a space that would otherwise fill entirely with water drawn from the same kind of aquifer we've just been following. For hundreds of thousands of years, before that chamber was ever pumped dry by any human effort, it sat completely submerged, filled with water, heated gently from below by magma resting in the crust nearby, water saturated almost to its absolute limit with dissolved minerals, sitting in near-perfect stillness for a length of time long enough for something extraordinary to grow. Inside that chamber are crystals of selenite, a form of gypsum, some of them stretching over 10 meters in length, beams of translucent crystal as long as a bus, growing at angles across the chamber the way beams of light might if light itself could somehow become solid and remain exactly where it fell. They formed the same basic way every mineral formation in this story has formed, through water slowly depositing dissolved material out of solution, except that here the conditions were close to perfect for an extraordinarily long, undisturbed stretch of time. A stable temperature, held steady by the magma nearby, warm enough to keep the water from cooling too quickly, and complete isolation from any disturbance at all. No flowing current, no seasonal change, nothing to interrupt the extremely slow and precise process of crystal growth across hundreds of millennia. Stand inside that chamber today, lit only by whatever artificial light has been brought in for the rare visit, and the crystals seem almost impossible, geometric shapes with perfectly flat faces and sharp, clean edges, stretching overhead and across the floor in directions that seem almost deliberate, almost engineered, though nothing about them was built by anything other than water and time and an unusually long stretch of uninterrupted stillness. Other crystal caves around the world, less extreme in scale but no less remarkable in their own way, form through similar patience under different specific conditions. Caves where groundwater rich in calcite has been left undisturbed long enough to grow crystal formations across cave walls in glittering sheets, catching and scattering any light that reaches them into countless small points, as if the walls themselves had been dusted with something that doesn't quite belong to ordinary stone. What unites nearly all of these formations, whether a single towering crystal beam or a wall glittering faintly with countless smaller ones, is the same basic requirement running beneath everything we've explored in this part of the journey so far: stillness, time. Water left alone long enough, and consistently enough, to slowly become something other than water, leaving behind, in exchange for its patience, a structure that will likely still be standing in that same dark chamber long after everything happening on the surface right now has been forgotten, replaced, and forgotten again. Beneath the ground, water is still moving through the pores of a sandstone aquifer somewhere at the pace of a few meters each year, carrying rain that fell long before this sentence was written. A sea note somewhere on the Yucatan Peninsula is holding its blue light as quietly today as it did yesterday, roots still reaching toward water they may never actually touch. A blue hole out at sea is resting in its layered stillness, warm water above, cold water below, indifferent to the boats passing over its opening in the afternoon sun, and somewhere in a sealed, still chamber deep beneath the ground, mineral is settling onto crystal, one nearly invisible layer at a time, continuing a project that will not be finished by the time anyone alive today has lived out their life. We'll go somewhere else in the dark next, following the faint, quiet glow of a light that isn't sunlight at all, produced by living things that have found a way to shine on their own in caves where no other light has ever reached. Not every dark chamber underground stays entirely dark. In a small number of caves scattered across the world, mostly in damp limestone country where still air and constant moisture create exactly the right conditions, a visitor rounding a corner in total blackness will sometimes look up and see something that, for a moment, doesn't seem to belong underground at all. Points of pale blue-green light, scattered across the ceiling in loose clusters, some close together, some drifting apart into open darkness, resembling nothing so much as a night sky, complete with something that looks almost like constellations, hanging directly overhead in a place the actual sky has never once reached. This light belongs to a small creature, technically not a worm at all, but the larval stage of a fly, that has found a way to produce its own glow through a chemical reaction inside its own body, a soft, continuous light with none of the flicker of a candle or the harshness of any artificial bulb, simply steady, undemanding, and still the way nearly everything else in this underground world tends to be. Each larva spins a nest along the cave ceiling and hangs from it a series of fine, sticky threads, sometimes a few centimeters long, sometimes considerably longer, dangling straight down into the open air of the passage below like an impossibly delicate curtain of silk. The glow itself is produced at the rear of the larva's body, a soft light bright enough to be seen clearly in complete darkness, but never so bright that it illuminates anything beyond its own immediate presence. The reason for the glow has nothing to do with beauty. of course, however beautiful it happens to look to a person standing beneath it. Small flying insects drifting through the cave, following faint air currents in the dark, are drawn toward the light the way insects are drawn toward any point of brightness in an otherwise black world. They fly toward it, become caught on one of the sticky hanging threads, and the larva, feeling the small vibration through the silk, draws its meal upward toward its waiting mouth. It's a trap built entirely out of patience and light, no different in its basic logic from many of the mineral formations we've already passed through on this journey. A structure requiring almost nothing from its surroundings beyond calm and time, doing its work in the dark without any awareness that anyone might ever stand beneath it and call it beautiful. Viewed from below, in one of the larger galleries where thousands of these small creatures have made their homes across a single ceiling, the effect really can resemble a clear night sky more than almost any other underground site in the world. Boats carrying visitors through some of these caves in complete silence, engines cut, drifting on still water beneath the glowing ceiling, offer one of the closest experiences available anywhere on Earth to floating beneath open stars while remaining, in every physical sense, deep inside solid rock with no sky above at all. The light these larvae produce comes from a chemical process called bioluminescence, the same basic principle responsible for the glow of certain deep-sea fish, some jellyfish, and a handful of other creatures scattered across environments where sunlight either never reaches or reaches so faintly that producing your own light becomes a genuine advantage rather than an unnecessary luxury. Two chemicals inside the creature's body react with each other, releasing energy as light rather than as heat, an efficiency of a kind that human-made light bulbs, wasting the vast majority of their energy as warmth, have never quite managed to match. What's worth sitting with, watching that glow from below, is how much it resembles something we already know intimately from the surface world, produced by a process that has nothing at all to do with fire or electricity or the sun. Life, finding itself in a place with no light at all, simply made its own. Not out of any need for beauty, but because in the darkest and stillest environments on the planet, a small point of glow, however humble its purpose, can mean the difference between finding a meal and going without one. Leave that glowing ceiling behind, and the underground world begins, gradually, to change character again, moving away from limestone, away from the slow chemistry of dissolving and redepositing rock into something built instead by heat rather than by water. Somewhere far beneath your feet, deeper than any cave we've explored so far, deeper even than most aquifers, rock exists in a state that behaves less like stone and more like something caught between solid and liquid, waiting for the right conditions to break through toward the surface. This is the volcanic underground, and it begins not with an eruption, which is really only the briefest and most visible part of a process that unfolds mostly out of sight, but with heat rising steadily from deep within the planet, gathering in pockets of partially molten rock that geologists call magma chambers. A magma chamber isn't a cave in any sense we've used the word so far. It isn't an empty space at all. It's a body of rock, sometimes stretching for many kilometers in every direction, that has been heated enough by the planet's interior to soften and partially melt, existing as a slow-moving mixture of liquid rock, semi-solid crystals, and trapped gas, all held under enormous pressure by the solid rock pressing in around it from every side. Picture, for a moment, honey left in a jar in a cold room, thick and barely moving even when tilted. Now picture that same honey gently warmed, loosening slightly, still far from any kind of liquid you'd recognize as pourable, but no longer entirely rigid either. Magma exists somewhere in that same range of behavior, though at temperatures reaching into the hundreds and even low thousands of degrees, capable of flowing, however gradually, in response to the pressure and heat surrounding it, without ever losing its fundamental identity as something closer to rock than to any liquid found at the surface. Beneath certain regions of the world, these chambers are unusually large, unusually shallow, or unusually persistent, feeding volcanic activity that has continued off and on for extraordinarily long stretches of geological time. Beneath the Yellowstone region of the western United States lies one of the most closely studied of these systems anywhere on the planet, a reservoir of partially molten rock resting a few kilometers below the surface, fed from deeper, still by an unusually persistent plume of rising heat from far within the mantle. The surface signs of everything happening beneath Yellowstone are visible to anyone who visits. Geysers throwing boiling water skyward on a schedule dictated entirely by underground plumbing, hot springs holding water in colours so vivid they seem almost artificial, ground that stays warm to the touch even through the coldest winter nights. But every one of these surface features is only the faint, visible edge of something enormous happening far below, heat rising from a chamber of partially molten rock that has been active, in one form or another, for a span of time longer than the current shape of the surrounding landscape has even existed. The pressure inside a system like this builds constantly. Gases dissolved within the magma, pushing outward against the surrounding solid rock, the same way carbon dioxide pushes against the inside of a sealed bottle, waiting for any crack, any weakness, any path of least resistance that might allow some of that pressure to finally escape. Most of the time, that pressure simply continues building and releasing in small, unremarkable ways. A slight swelling of the ground here, a shift in the temperature of a hot spring there, changes so gradual that instruments installed specifically to detect them often struggle to distinguish genuine movement from ordinary background noise. Occasionally, though rarely, on a timescale that dwarfs even the unhurried rhythms we've encountered so far in caves and aquifers, that pressure finds a path all the way to the surface, and the result is an eruption. Magma forcing its way upward through weaknesses in the crust, releasing the heat and gas that had been accumulating, sometimes gently, sometimes catastrophically, depending entirely on how much pressure had built and how suddenly it managed to escape. But eruptions, dramatic as they are, represent only the briefest possible moment in an underground story that otherwise unfolds with almost total silence and no urgency whatsoever. For every eruption that ever occurs anywhere on Earth, there are magma chambers that have sat beneath the surface for thousands of years without producing any visible activity at all, cooling by degrees, shifting almost imperceptibly, occasionally being recharged by fresh heat rising from even deeper within the planet, existing the entire time in a state of quiet balance that most of the world above never has any reason to think about. Where magma does find its way to the surface, whether through a dramatic eruption or through a much gentler, more continuous seep, it doesn't always behave the way popular imagination tends to picture it. Not every eruption produces a violent explosion. In many places, magma reaches the surface as lava, flowing rock that has lost enough pressure and gas to move as a relatively calm, continuous stream rather than an explosive burst, spreading across the landscape the way a slow-moving river of fire might spread across a floodplain. And it's here, in the behavior of flowing lava rather than exploding magma, that another kind of underground world begins to take shape. One built not out of dissolving limestone over hundreds of thousands of years, but out of cooling rock over a matter of hours or days, a process so much faster than anything else in this journey that it can feel almost startling by comparison. Picture a river of lava moving across open ground, glowing softly in shades orange and red at its surface, radiating heat strong enough to be felt from a considerable distance. As that lava moves, its outer surface, exposed directly to the cooler air above, begins to cool and harden almost immediately, forming a thin crust across the top of the flow, even while the lava underneath that crust remains liquid, still moving, still hot, insulated from the outside air by the very rock it has just finished forming. This hardened crust acts almost like a roof, a natural covering that keeps the lava beneath it from losing heat as quickly as it otherwise would, allowing the still molten rock underneath to continue flowing onward, sometimes for a considerable distance, long after the surface above it has cooled solid enough to walk across if anyone were foolish enough to try it while the flow was still active. Eventually, once the supply of fresh lava feeding the flow slows and then stops entirely, whatever liquid rock remains inside that hardened outer crust drains onward and away, following gravity toward wherever the ground continues to slope downward, leaving behind an empty tunnel exactly the shape and size of the river of lava that once flowed through it. Solid rock above, solid rock below, solid rock on every side, and in between, nothing but open air where liquid stone used to be. This is a lava tube, and it stands in almost complete contrast to every cave we've explored so far in this journey. A limestone cave takes shape over tens of thousands of years, sometimes millions, through the slow chemical dissolving of rock by faintly acidic water. A lava tube can take shape in a single eruption, sometimes forming within a matter of hours, the entire process from flowing liquid rock to hollow solid tunnel complete before the surrounding landscape has even finished cooling from the heat of the eruption that created it. Walk into a lava tube in the places around the world where they're accessible enough for visitors, and the rock around you looks and feels entirely different from anything found in a limestone cave. Instead of smooth, pale walls shaped by dissolving and redeposit, the surface here tends toward dark, rough, sometimes glassy stone, still bearing the visible texture of the moment it stopped flowing and hardened permanently in place. In some tubes, the walls carry a distinct high water mark, a visible line showing exactly how deep the river of molten rock was flowing at its peak before it drained away and left the tunnel empty, the same way a flood leaves a mark on a riverbank long after the water itself has receded. The ceilings of lava tubes sometimes carry their own strange formations, distant cousins of the stalactites found in limestone caves but built through an entirely different, much faster process. As the lava tube was still forming, droplets of molten rock occasionally dripped from the cooling ceiling before fully hardening, leaving behind small, glassy points called lavasicles. Shaped remarkably like stalactites, pointed and tapering, but formed not across tens of thousands of years of mineral deposit, instead solidifying within moments as the entire tube itself was cooling from its original molten state. Some lava tubes stretch for remarkable distances, following the original path the lava took as it moved downhill from its source, sometimes for many kilometers, occasionally branching where the original flow split around some obstacle in the landscape or drained through multiple paths at once. Where sections of a tube's roof are thin enough, they can collapse long after the lava has fully cooled and drained, exactly the way limestone cave ceilings sometimes collapse to form a C-note, opening a window down into the tunnel from the surface above and letting daylight and, eventually, plant roots and small animals find their way into a passage that had been completely sealed since the moment it finished forming. There is something worth noticing in how differently these two kinds of underground worlds carry their own history. A limestone cave records centuries in the gradual growth of a single stalactite, each ring of mineral, a quiet testimony to time passing far above at a pace no visitor could ever directly witness. A lava tube records something closer to a single dramatic afternoon, frozen permanently in place. The exact shape the lava happened to be moving through at the precise moment it stopped, preserved in solid rock ever since, changing very little over the millennia that followed. And yet, despite forming through an entirely different process on an entirely different timescale, a lava tube settles, once its formation is complete, into much the same kind of stillness found everywhere else underground in this story. The heat that once filled it fades over the following years and decades until the tunnel eventually reaches the same steady, muted temperature found in any deep cave, insulated the same way by the rock surrounding it, cut off from the daily and seasonal swings of surface weather in exactly the same fashion as a limestone chamber that took 100,000 years to form rather than a single day. Beneath the ground in volcanic regions all over the world, this same basic process has repeated itself again and again across countless eruptions throughout geological history, leaving behind networks of lava tubes stacked in layers, some ancient and long since collapsed or filled with sediment, others remarkably intact, waiting in the dark exactly as they were left the moment the last of their molten contents drained away and allowed them to finally cool and settle. Follow the heat that created these tunnels back toward its source, rather than following the tunnels themselves outward across the landscape, and you arrive at something that never quite goes away, even in places where no eruption has occurred for a very long time, and none seems likely again anytime soon. Heat, rising continuously from deep within the earth, seeking any path it can find toward the cooler surface above, whether or not any magma happens to be involved in that particular journey at all. This is geothermal heat, and unlike the sudden, dramatic story of an eruption, it represents something closer to a constant, quiet exhale from the planet itself, present everywhere beneath the surface to one degree or another, occasionally concentrated enough in certain locations to produce some of the most visibly strange and beautiful features found anywhere on the surface of the Earth, where groundwater happens to seep down close enough to a source of underground heat, whether a cooling magma chamber or simply rock naturally warmer than usual due to its depth and composition, that water is warmed from below the same way a pot of water is warmed from below on a stove, except far more gradually and far more continuously over a period of time that might stretch across centuries rather than minutes. Warmed water is generally less dense than the cooler water surrounding it, and so it tends to rise, the same way warm air rises through cooler air, seeking any available path back toward the surface. Where that path happens to open into a pool or spring, the result is a hot spring, water emerging at the surface already heated by its journey through the rock below, sometimes warm enough to be comfortable for bathing, sometimes hot enough to be genuinely dangerous, depending entirely on how close its underground path happened to bring it to whatever heat source was warming it in the first place. In certain rare conditions, the underground plumbing feeding one of these hot springs includes a particular kind of constriction, a narrow point in the rock through which water and steam must pass before finally reaching the surface. Where this constriction exists, pressure can build in the chamber below it the same way pressure builds inside a covered pot of boiling water, until eventually that pressure exceeds what the narrow opening above can release calmly, and the entire system erupts all at once, throwing a column of boiling water and steam high into the air before the pressure equalizes and the whole cycle begins building toward its next release. This is a geyser, and the most famous examples, found in a small handful of locations scattered across the world, have been erupting on a schedule steady enough to draw visitors who arrive specifically to watch a single, brief performance repeated with only minor variation across an interval that has held roughly consistent for as long as careful records have been kept. Underground, none of that performance requires any awareness at all. The chamber fills, the pressure builds, the narrow throat above eventually releases what it can no longer hold back, and then, without any sense of accomplishment or rest, it begins filling again. Not all geothermal heat rises through water at all. In certain volcanic regions, heat escapes more directly, rising as steam through cracks and vents in bare ground, sometimes accompanied by the faint smell of sulfur where volcanic gases mix with the escaping vapor. These vents, called fumaroles, can persist for centuries in the same fixed locations, marking spots where the underground plumbing happens to offer heat and gas a clear path upward, the ground around them often stained pale yellow or rust orange by mineral deposits left behind as the gases cool and react with the air. Walk across ground like this on a cold morning, and the sight can be almost eerie in its quiet insistence. Steam rising steadily from bare rock in dozens of separate points across an open field. No fire visible anywhere, no obvious source for any of the heat, just vapor drifting upward from the ground itself, as though the earth were breathing out into air cold enough to make that breath visible. Humans have made use of this underground heat for a very long time, channeling hot spring water into pools for bathing, and in more recent history, drilling wells specifically to draw up naturally heated water and steam to warm homes, generate electricity, or supply greenhouses through winters that would otherwise be far too cold for the crops grown inside them. In certain countries sitting directly atop unusually active geothermal regions, a significant share of all the electricity and heating used by the entire population traces back to nothing more than this same constant leak of heat rising from deep underground, present the entire time regardless of whether anyone above ever thought to make use of it. What ties every part of this volcanic underground together, whether we're talking about a magma chamber resting beneath the surface for centuries, a lava tube frozen in the exact shape of a single day's eruption, a hot spring rising gently from below, or a geyser building toward its next release, is heat that ultimately comes from the same place. The deep interior of the planet itself, still radiating. Warmth left over from the Earth's formation, still generating fresh heat through the decay of radioactive elements buried far below anything we've explored so far in this journey. That heat doesn't stay contained to isolated chambers and vents. It's connected to something much larger, a vast, continuous movement of rock occurring far beneath the crust we've spent this entire journey standing on. A circulation that has been driving nearly everything we've encountered so far, without most of us ever realizing it was happening at all. That's where we'll go next. Down past the deepest lava tube, past the deepest magma chamber, into the mantle itself, where rock doesn't dissolve and doesn't cool into tunnels, but instead flows, gradually, across spans of time so long that a single circulation might not complete itself before the mountains above have already risen and worn away again. For now, let the quiet steam of a fumarole settle in your mind, rising steadily from bare ground into cold morning air, unhurried and constant, expecting nothing from anyone standing nearby, continuing exactly as it has continued for longer than anyone has been counting. Beneath every magma chamber, beneath every hot spring and every fumarole leaking its slow breath into cold morning air, lies the source that feeds all of it. Not a single pocket of heat, but an entire layer of the planet, thousands of kilometers thick, made of rock that behaves in a way almost nothing at the surface prepares you to imagine. This is the mantle, and it makes up the overwhelming majority of the Earth's total volume, dwarfing the thin crust we've spent this whole journey moving through the way an ocean dwarfs a single wave crossing its surface. If the crust is the planet's skin, thin and brittle and endlessly varied from place to place, the mantle is everything beneath that skin, a vast, mostly solid body of rock that nonetheless moves, slowly and continuously, in a way the surface rock never does. The word solid deserves a little unpacking here because it can be misleading. Mantle rock is not molten. It is not lava, and it is not the same soft, partially liquid material found inside a magma chamber closer to the surface. Under ordinary conditions, if you could somehow hold a piece of it in your hand, it would feel exactly like solid stone, because that's precisely what it is. And yet, given enough time, and enough pressure, and enough heat, that same solid stone behaves less like a rigid object, and more like something that can bend, stretch, and slowly flow, the way a bar of solid metal held in place for centuries under enough weight might very gradually sag rather than shatter. Think of cold honey, thick and barely moving, even when the jar holding it is tilted on its side. Left completely still, that honey looks solid enough to hold its shape indefinitely. But given enough time and enough persistent pressure, it does eventually move, flowing downward in response to gravity at a pace too slow to see directly but unmistakable if you return to check on it after enough time has passed. Mantle rock behaves in much the same way, though at a scale and pace that makes cold honey look almost frantic by comparison. Individual portions of it can take somewhere in the range of 1 million years to complete a single, significant movement from one location to another, a stretch of time so vast that no human observation, however patient, could ever hope to witness it directly. And yet that movement, however slow, never actually stops. Deep within the mantle, heat rising from the planet's core warms rock at the bottom of this enormous layer, causing it to become very slightly less dense than the rock surrounding it. That slightly warmer, slightly lighter rock begins drifting upward through the layers above it, the way a warm bubble might rise through a pot of very thick, very slow-moving liquid. As it nears the top of the mantle, closer to the crust, it cools, becomes denser again, and eventually begins sinking back downward, completing a great, slow loop that geologists call convection. This convection is not a single, simple cycle occurring uniformly across the entire planet. It happens in numerous separate cells, some larger, some smaller, rising and sinking in different regions at different rates. An enormous, layered, endlessly complex circulation that has been running continuously, in one form or another, for the entire span of time the Earth has possessed a solid crust at all. What makes this slow, largely invisible movement worth pausing over is what it actually does to everything above it. The crust of the Earth doesn't float on the mantle the way a boat floats on water, exactly, but it does rest directly on top of this circulating layer, broken into the great plates we encountered right at the very beginning of this journey, each one riding along, gradually, wherever the currents beneath it happen to be moving. This is the true engine behind everything we explored on the surface earlier tonight. The reason continents drift apart and collide with each other across the surface of the Earth, the reason mountain ranges rise where two plates happen to meet and press against each other, the reason ocean floors are constantly being created in some places and destroyed in others. None of it originates at the surface at all. Every single one of those surface events is simply the visible outcome of something happening far below, in rock flowing so slowly that its motion could never be directly felt, only inferred over time from its consequences. Picture, for a moment, standing on a beach somewhere, watching waves roll steadily toward the shore. The waves themselves are visible and immediate, each one arriving, breaking, and retreating within the space of a few seconds. But the wave is only the surface expression of something happening far out at sea, wind moving across open water, transferring its energy downward in a way that eventually produces the visible motion breaking against the shore in front of you. The mantle's convection works on a similar principle, except stretched across a timescale so enormous that a single complete cycle, from rising warm rock to sinking cool rock and back again, might take longer than the entire history of complex life on the surface above it. There is a particular kind of vertigo in trying to hold both of these timescales in your mind simultaneously. A wave breaking on a beach takes a few seconds to complete its journey from open water to shore. A single cycle of mantle convection might take on the order of tens or hundreds of millions of years. And yet both are, in their own way, the same basic kind of motion. Energy moving from a place with more heat toward a place with less, patiently, continuously, without needing anyone to notice or measure it in order to keep happening. Where this slow circulation brings two plates together at the surface, rather than pulling them apart, something happens that we touched on only briefly earlier in this journey, and that deserves a slower, closer look now that we've descended far enough to properly understand what's actually driving it. When an ocean plate, dense and heavy from its volcanic composition, meets the edge of a lighter continental plate, or even another ocean plate that happens to be slightly less dense, it doesn't simply stop and pile up against it. Instead, following the pull of gravity and the deep currents of the mantle beneath it, the denser plate begins to bend downward, sliding beneath the lighter plate above it and slowly descending back down into the mantle from which, in a sense, it originally came. This is called subduction, and it represents one of the most significant recycling processes on the entire planet, returning old, cooled crust back into the depths from which new crust is constantly being created elsewhere at the cracks and ridges where plates are pulling apart rather than colliding. The descent itself is neither fast nor smooth. As the plate sinks, it drags against the rock around it, generating tremendous friction and pressure along the boundary where the two plates meet. Much of the time, that boundary holds firm, locked in place by friction, storing up strain the same way a tightly wound spring stores up tension, waiting for a point of weakness or a slight shift that will finally let it release. When that release finally comes, it happens fast, in stark contrast to nearly everything else in this underground story. A section of the boundary that had been locked for years, sometimes for centuries, suddenly gives way, the two plates slipping relative to each other in a matter of seconds, sending shockwaves through the surrounding rock that we feel at the surface as an earthquake. Some of the largest and most powerful earthquakes ever recorded have occurred along exactly these kinds of subduction boundaries, releasing, in a single brief moment, energy that had been slowly accumulating underground for a length of time that dwarfs any human memory of the region's supposed calm. As the descending plate continues its slow journey downward, deeper into the mantle, it carries with it water trapped inside its minerals, water that originally came from the ocean floor sediments and hydrated rock accumulated over the plate's long existence before it ever began sinking. Under the enormous heat and pressure found at these depths, that trapped water is released over time, and where it rises into the hot rock above the descending plate, it lowers the melting point of that surrounding material, encouraging it to partially melt and form fresh magma, exactly the kind of magma we encountered earlier, feeding volcanic mountain ranges and chains of active volcanoes scattered along nearly every subduction zone found anywhere on Earth. In this way, subduction connects nearly everything we've explored in this journey into a single continuous, if extraordinarily slow, cycle. Ocean crust forms at a ridge, spreads outward across the seafloor over millions of years, eventually reaches a subduction zone, sinks back down into the mantle, releases water that helps generate fresh magma, and that magma rises to feed new volcanoes and, eventually, new crust, closing a loop that has been running continuously for a length of time, reaching back further than nearly anything else discussed so far tonight. It is inside this same deep, hot, slow-moving world that some of the most valuable materials found anywhere on Earth take shape, formed not through the dissolving and redepositing of limestone we saw in caves, and not through the rapid cooling of lava we saw in volcanic tunnels, but through an entirely different combination of extreme heat, extreme pressure, and mineral-rich fluids moving through rock, over spans of time that once again stretch well beyond ordinary human comprehension. Deep within the crust, particularly in regions where magma has intruded upward from below without necessarily reaching the surface, hot fluids rich in dissolved metals and minerals circulate slowly through cracks and fractures in the surrounding rock, cooling gradually as they move further from their heat source and depositing, as they cool, the dissolved material they had been carrying. Given enough time, these deposits can accumulate into significant concentrations of valuable minerals. Veins of gold, silver, copper, and other metals running through solid rock like threads through fabric, each one representing a very long, very patient process of hot fluid, slowly giving up what it once carried in solution, exactly the same basic principle that built every stalactite and every crystal chamber we passed through earlier in this journey. Adapted here to a very different set of underground conditions and a very different set of materials. Diamonds, among the most prized of all materials found underground, form under conditions even more extreme than these veins of metal, requiring pressure and heat found only very deep within the mantle itself, far below where most other mineral formation processes occur. Carbon, subjected to these extraordinary conditions for spans of time that can reach billions of years, gradually rearranges its internal structure into the dense, tightly bonded crystal lattice that makes a diamond so exceptionally hard and so capable of bending light into the particular brilliance that has fascinated people for as long as diamonds have been found and collected. These diamonds only ever reach the surface at all through a particular, relatively rare kind of volcanic eruption, one that originates far deeper than most ordinary volcanic activity, punching upward through the crust quickly enough to carry diamonds and other deep mantle material with it before they have time to be altered or destroyed by the journey. The resulting formations, called kimberlite pipes after the South African town where they were first properly studied, represent some of the only natural pathways by which material from hundreds of kilometers beneath the surface ever makes its way up to where a person might actually hold it in their hand. There is something worth sitting with in the idea that a diamond, small enough to rest on a fingertip, might represent both an almost unimaginable span of time spent forming deep within the mantle and an almost impossibly narrow, violent window of opportunity that finally brought it up to the surface where it could be found at all. Nearly everything about its story took ages to unfold in complete darkness, deep underground, and only the very last, briefest chapter of that story happened quickly, and by comparison, almost recently. Not every underground treasure takes quite so violent a path to the surface. Opal forms far more gently, in shallow cracks and cavities where silica-rich water seeps through sedimentary rock and slowly deposits microscopic spheres of silica, layer upon layer, over a period that can stretch across many millions of years without ever involving heat or pressure anywhere close to what a diamond requires. The particular play of color inside a fine opal, shifting and flashing as it's turned in the light, comes entirely from the precise, orderly arrangement of those microscopic spheres. A structure fine enough to bend light into color the way a prism does, built by nothing more dramatic than groundwater moving patiently through rock, exactly the same quiet chemistry responsible for so much of what we've already seen on this journey, simply arranged, in this one particular case, into something a person might eventually wear as jewelry. Human beings have been drawn toward this underground world of hidden minerals for a very long time, digging, tunneling, and searching for exactly these kinds of deposits, since long before anyone had any real understanding of how they had actually formed. The earliest mines were often little more than shallow pits or short tunnels, dug by hand into deposits visible at or near the surface, gradually extended deeper as the easily accessible material ran out and the search for more required following a vein further down into the rock. Over time, this search for underground resources became inseparable from a broader human curiosity about the underground world in general, one that extended well beyond the simple pursuit of valuable minerals into something closer to genuine exploration for its own sake. Long before scientific cave mapping existed in anything like its modern form, people were entering caves for shelter, for ritual, for burial, leaving behind traces of their presence in the form of paintings on cave walls, tools left behind in dry chambers, footprints preserved in soft mud that has remained undisturbed for tens of thousands of years since the last person to walk through that particular passage moved on and never returned. Some of the oldest surviving artwork made by human hands is found not in the open air, where wind and rain would have erased it within a matter of centuries, but deep inside cave systems, in chambers far enough from any entrance that the stable, protective conditions we explored earlier in this journey, the cool, steady temperature, the still air, the absence of any real weathering at all, allowed pigments applied to a cave wall tens of thousands of years ago to survive essentially unchanged until the moment someone finally rediscovered them. Standing in front of one of these ancient paintings, deep inside a cave that has otherwise remained completely unchanged for the entire span of time since the artist finished their work and left, produces a particular kind of quiet that's difficult to find anywhere else. The painting has been waiting there, in the dark, for a length of time that makes nearly every other measure of human history feel almost recent by comparison, protected not by any deliberate effort, but simply by the same stillness and isolation that protects every other fragile, patient thing we've encountered on this journey so far. Modern cave exploration, the deliberate and systematic mapping of underground passages purely for the sake of understanding what's actually down there, is a considerably more recent pursuit, and it remains, even today, a genuinely unfinished project. Vast stretches of the world's known cave systems remain entirely unmapped, their full extent unknown even to the researchers who have spent years exploring them, simply because a cave system can branch and narrow and open into new passages faster than any team of explorers working with whatever equipment and time they have available can hope to fully chart. The deepest caves currently known to exist on the planet, most of them found in mountainous limestone regions where the rock has had ample opportunity to fracture and dissolve across a considerable vertical distance, plunge for well over 2 kilometers below their highest entrance, a depth that requires days of continuous travel simply to reach the bottom and days more to return, moving through passages that range from spacious chambers large enough to hold a cathedral to narrow crawl spaces barely wide enough for a single person to squeeze through while wearing full equipment. Explorers who have spent extended stretches of time at these extreme depths describe an experience of isolation almost impossible to replicate anywhere else on the surface of the Earth. Cut off not only from daylight and from any contact with the world above, but often from any reliable means of quick return should something go wrong far below. The silence at these depths is, if anything, even more complete than the silence found in the shallower caves we explored earlier in this journey. A stillness so absolute that some explorers report a kind of sensory disorientation, the mind struggling to process an environment, offering it almost nothing at all to register beyond the narrow beam of a headlamp and the sound of their own careful breathing. Not every underground void announces itself in advance the way a cave entrance does, opening quietly on a hillside for anyone who happens to notice it. Some voids stay completely hidden until the moment the ground above them simply stops holding their weight. This happens most often in the same kind of karst landscape we followed earlier in this journey, where limestone has been dissolving slowly beneath the surface for a very long time, leaving behind hollow chambers and widened cracks that may sit just beneath a covering of soil thin enough that nothing above ever gives any warning that emptiness lies below. The soil holds. The grass grows, a road gets built across it, or a house, or a field gets planted and harvested for generations, all resting on a roof of soil and thin rock that has been slowly weakening from underneath the entire time, dissolving by fractions too small to notice in any single season. And then, sometimes without any warning that a person standing there would ever have caught in time, the roof gives way. A sinkhole can open gradually, the ground above a slowly dissolving cavity settling and sagging over the course of weeks or months, a shallow depression appearing in a lawn or field that deepens gradually enough for someone to notice and step carefully around it long before it becomes dangerous. But it can also open suddenly, catastrophically, an entire section of ground collapsing within seconds into a void that had been quietly widening beneath it for centuries, swallowing whatever happened to be resting on the surface at that exact moment with no warning at all beyond, perhaps a faint groaning sound in the ground moments before it gave way. In certain regions built on especially soluble bedrock, sinkholes are common enough to be treated as an ordinary, if unwelcome, feature of the local landscape, tracked by geologists the way a coastal region might track the slow erosion of its shoreline. Entire neighborhoods have been built, unknowingly, above ground weakened this way, the danger invisible for years, sometimes decades, until one particular section of one particular yard finally reaches the point where the rock above its hidden cavity can no longer bear the weight resting on it. Standing at the edge of a freshly opened sinkhole, looking down into a chamber that had been sealed and hidden for centuries before the ground above it finally failed, offers a different kind of view into the underground world than any sea note or blue hole we explored earlier. There is no gentle blue water waiting below, no birds nesting in the rim, no dangling roots reaching down towards something they need. Just raw, broken earth, and beneath it, the abrupt, unglamorous exposure of a hollow space that had been part of this hidden system all along, quietly widening over centuries, patiently waiting for the exact moment the ground above finally ran out of strength. And yet, even a sinkhole eventually settles into the same stillness that governs everything else underground in this story. Once the initial collapse is finished, once the loose soil and broken rock have found their resting angle at the bottom of the new opening, the chamber it exposes returns to its familiar quiet, the same cool, steady air settling into it that settles into every other cave chamber we've passed through tonight, indifferent now to whatever surface disruption its sudden appearance might have caused only moments before. Not every underground environment on Earth remains warm and stable, however. In certain regions, particularly toward the planet's poles and at high elevation, the ground itself has been frozen solid for a length of time stretching back not centuries, but in some places tens of thousands of years, forming an entirely different kind of underground world, one shaped not by heat and dissolving rock, but by cold so persistent that it has fundamentally altered the ground itself. This is permafrost, ground that remains frozen continuously for at least 2 consecutive years. Though in the most extreme regions, that continuous frozen state has persisted, essentially unbroken, since long before the last ice age fully receded. Beneath a thin surface layer that does thaw briefly each summer, permafrost extends downward, in some locations, for many hundreds of meters. A vast, frozen archive holding within it materials that have remained essentially unchanged since the very day they became trapped in ice. Preserved within permafrost in various parts of the world, researchers have found the remarkably intact remains of animals that died tens of thousands of years ago, in some cases with soft tissue, fur, and even stomach contents still intact, offering a level of detail about ancient ecosystems that fossils formed through ordinary mineral processes almost never provide. It is a strange kind of preservation, entirely different from the slow mineral transformation we saw earlier, turning shell into limestone and limestone into marble. Nothing here has been replaced or transformed at all. It has simply been paused, held in place by cold so constant and so persistent that decay itself has been almost entirely suspended for a length of time longer than human civilization has existed in any recognizable form. Beneath this frozen crust, in pockets where the ice has never fully sealed away every trace of moisture, scientists have found something else worth pausing over. Microorganisms, frozen for tens of thousands of years, that can, under the right laboratory conditions, be gently revived, returning to activity after a pause in their biological activity longer than almost anything else known to survive. Dormancy of any kind. It suggests a strange kind of patience even here, in ground too cold for almost anything else to continue functioning at all, life simply waiting, suspended, for a warmth that may or may not ever come again. And yet, even in these deepest, most isolated chambers, and in this oldest, most persistent ice, life still finds a way to persist, in forms often so specialized, so completely adapted to their particular corner of permanent darkness or permanent cold that they exist nowhere else on the surface of the planet at all. Beyond the blind fish and pale crustaceans we encountered earlier, in the deepest and most isolated cave systems studied so far, researchers have found entire ecosystems functioning without any reliance whatsoever on sunlight, a discovery that quietly reshaped a great deal of scientific understanding about what life actually requires in order to survive. Certain bacteria, living on the walls of these deep chambers, derive their energy not from sunlight at all, unlike almost every ecosystem at the surface, but instead from chemical reactions involving minerals dissolved in the surrounding rock and water, a process called chemosynthesis that allows life to sustain itself entirely independent of any connection to the sun. These bacterial colonies, in turn, support small populations of other cave-adapted creatures that feed on them, forming a complete, self-sustaining food chain existing in permanent darkness, disconnected from the surface world in nearly every meaningful sense except for the water that occasionally seeps down to sustain it. Some of these ecosystems have likely existed in near-total isolation for a length of time reaching back many millions of years, their inhabitants evolving generation after generation in conditions so stable, so unchanging, that entire evolutionary lineages have persisted essentially unchallenged by the kind of environmental pressure and change that shapes life so dramatically at the surface. It leaves us with one quiet, genuinely strange thought worth considering as you drift here tonight. Life, it turns out, doesn't need the sun at all in order to exist. It only needs energy in some usable form and enough stability to make use of it. Sunlight happens to be the most abundant and obvious source of that energy across most of the surface of this planet. But underground, in certain rare and stable pockets, life has quietly found other ways, other sources, other paths entirely disconnected from the sky, continuing on in the dark exactly as patiently as everything else we've encountered so far on this journey. Beneath this frozen ground, and beneath the deepest caves, and beneath even the descending plates of the subduction zones we traced earlier, the mantle continues its own slow work exactly as it always has, indifferent to whether the ground far above happens to be frozen, solid, or scorched by a nearby volcano, continuing its vast, patient circulation regardless of whatever happens on the thin, varied surface so far above it. And somewhere within that mantle, at a depth most people never learn exists at all, lies one final discovery worth carrying with us as this journey begins, gently, to make its way back toward the surface. A layer of rock, deep and hot and under pressure almost impossible to properly imagine, that appears to hold within its own crystal structure an amount of water that may rival or even exceed every ocean resting on the surface of the earth combined. That's where we'll go next, into the very deepest point this journey will reach, before we finally begin our slow return upward, back through everything we've already passed, toward the surface and toward sleep. For now, let the cold stillness of frozen ground settle over you, and beneath it, imagine the mantle, moving at its own extraordinarily slow pace, carrying everything above it forward, one almost imperceptible shift at a time, exactly as it has for longer than this story could ever fully hold. Deep within the mantle, far beneath the caves, underground rivers, and aquifers we've followed so far, a mineral exists that very few people have ever heard of, and yet it may be one of the most important materials inside the Earth. It's called ringwoodite. Ringwoodite is, in its basic chemistry, not so different from the olivine that makes up much of the upper mantle we already described. The same iron and magnesium and silicon arranged into a crystal structure. But at this particular depth, roughly between 400 and 600 kilometers below the surface, the pressure becomes so extreme that the atoms inside that crystal are forced into a different, denser arrangement entirely. A rearrangement that changes not just the physical shape of the mineral, but something else about it too, something that took scientists a long time to fully appreciate. Within this denser crystal structure, there is room, at a microscopic level, for water. Not water in the ordinary sense, not a pocket of liquid resting somewhere between grains of rock, but water broken down to its most basic chemical components and woven directly into the crystal lattice of the mineral itself, held there the way a single thread might be woven permanently into the structure of a piece of fabric, inseparable from the material around it without breaking the fabric apart. Entirely. For a long time, this was only a theory, tested in laboratories by recreating the same extreme pressure found at these depths and observing, in small manufactured samples, that ringwoodite really could hold water this way if given the chance. What remained uncertain for years was whether this same process was actually happening at scale, deep inside the real Earth, or whether it was simply an interesting possibility that never quite arose naturally. Then, after years of uncertainty, confirmation arrived from an unexpected place. Inside a diamond. Diamonds, as we discussed a little earlier in this journey, occasionally travel upward from tremendous depths through rare and violent volcanic eruptions, carrying with them small fragments of whatever rock happened to be nearby at the moment they were swept toward the surface. In one particular diamond, found in Brazil, and eventually studied by researchers specifically interested in what it might reveal about the deep mantle, a tiny fragment of ringwoodite was discovered trapped inside, sealed away from the moment the diamond formed until the moment scientists finally examined it centuries or millions of years later. That tiny trapped fragment, smaller than a grain of sand, contained water. Not much, in absolute terms, but enough, once properly measured and understood, to suggest something remarkable about the layer of mantle it had come from. If that single small sample was even roughly representative of the wider ringwoodite layer surrounding the entire planet at that same depth, then the total amount of water held within it, spread out across the whole globe, might be enormous. Comparable to the amount of water found in all of Earth's oceans combined, and perhaps even more. Sit with that for a moment, the way we've sat with so many other strange, quiet facts on this journey tonight. Every ocean you have ever looked at, every wave that has broken against every shore, every drop of rain that has ever fallen into the sea. Together they might represent only half, or perhaps even less, of the total water actually present on this planet. The rest, if this discovery holds up as further research continues to explore it, is not sitting on the surface at all, resting beneath an open sky. It is locked, molecule by molecule, into the crystal structure of a mineral most people will never see, hundreds of kilometers beneath the ground, in a layer of the Earth so hot and so pressurized that the water within it could never simply pour out or flow or do anything resembling what water does on the surface. It exists there in a form closer to a chemical component of solid rock than to water as we would ever recognize it standing at the edge of any ocean, lake, or underground river we've followed so far tonight. This hidden reservoir isn't motionless forever, either. Recall the plates we followed earlier, descending slowly into the mantle at subduction zones, carrying trapped water down with them from ocean floor sediment accumulated over millions of years. Some portion of that descending water, geologists believe, continues traveling downward far past the point where it triggers volcanic activity near the surface, sinking further still until it eventually reaches this same transition zone where ringwoodite forms, adding, however slowly, to whatever water might already be held there. And the reverse may happen as well. In certain regions where mantle rock rich in this water-bearing ringwoodite rises back upward, carried along by the same slow convection currents we traced earlier. As that rock rises towards shallower depths, the pressure holding the water in its dense crystal form gradually decreases. And at some point, the mineral simply can't hold onto its trapped water any longer, releasing it, transforming as it does into other, less dense minerals that have no room in their own structure for water at all. Researchers believe this slow release, happening continuously across the planet's history at the boundary of this deep transition zone, may play a quiet but genuinely important role in driving volcanic activity and mantle convection far above it, water working its way back toward the surface across a journey that might take many millions of years to complete, an echo on an almost unimaginably larger scale of the same basic pattern we traced earlier, watching rains sink into an aquifer and slowly, patiently find its way back to a spring somewhere far downhill. There is a strange kind of symmetry in that image, worth holding on to as we finally begin our way back up toward the surface tonight. At the very beginning of this journey, we followed rain falling gently onto soil, sinking down through rock, resting for a while in the quiet dark of an aquifer, and eventually emerging again through a spring, a river, or the sea. Here, at the very deepest point we've reached, the same basic pattern repeats itself, on a scale so much larger that it stretches the meaning of nearly every word we've been using to describe it. Water sinking. Water resting quietly inside solid rock for spans of time beyond ordinary imagination, and eventually finding its way upward again. The whole planet, considered this way, holds something like its own single, enormous, unhurried breath. Rain falls, soaks into the ground, moves through rock at every scale from a limestone cave to the deep mantle itself, and eventually, given enough time, makes its way back toward daylight, however long that particular journey happens to take. Some of it returns within a season. Some of it returns after centuries spent in a fossil aquifer. And some of it, sealed inside ringwoodite at the very edge of what we can currently measure or understand, may not return to the surface world at all for a length of time that makes even the oldest cave formations we passed through earlier in this journey seem almost young by comparison. This is the deepest point we will reach tonight. From here, there is nowhere deeper for this journey to follow. Not because the planet ends at this depth, because it certainly doesn't, continuing on through the lower mantle and eventually into the molten outer core and the solid inner core at the very center of the Earth, but because everything below this point moves so far beyond ordinary human experience in scale and pressure and temperature that it stops feeling like a place at all and starts to feel more like pure physics, stripped of nearly everything that has made this journey feel. Until now, like something you could actually stand inside and quietly observe. So we'll let this be the furthest point, and we'll begin, gently, the long way back. Imagine, now, rising slowly back up through everything we've already passed, not quickly, not with any urgency, simply drifting upward the way a very small bubble might rise through the same thick, slow honey we imagine the mantle to be, taking however long it needs to take. Up past the ringwoodite, its trapped water settling once more into stillness, past the descending plates of the subduction zones, still sliding slowly downward on their own patient schedule. Higher still, the deep mantle currents rising and sinking in their slow convecting loops, currents that will not complete a single visible cycle in the whole span of your life or your children's lives or theirs. Up past the magma chambers, up past the cooled lava tubes, Up past the hot springs we lingered beside earlier, where steam still drifts quietly into the morning air. Beyond the sinkhole, its raw edges softening slowly with each passing season, grass beginning to find its way along the rim. Then, past the frozen ground of the permafrost, holding its ancient, paused world just as it always has for longer than anyone has been alive to notice. Past the deepest caves, their silence complete, their explorers long since returned to the surface and asleep in their own beds somewhere far above. Beyond the veins of gold and the kimberlite pipe holding its diamonds, patient, unhurried, waiting the way everything down here waits, without any sense of waiting at all. Past the crystal chamber, its enormous beams of selenite resting exactly where they have rested for hundreds of thousands of years. Then the aquifer, water still moving through its tiny connected pores at the pace of a few meters each year, carrying rain that fell long before any of us were born. And finally the sea note, its blue water glowing quietly under whatever sky happens to be stretched above it right now. Past the underground river, still flowing through total darkness at its own quiet rhythm. Nearby, the stalactites and stalagmites still growing by fractions too small to see, one patient drop at a time. And the glowing ceiling of the cave we visited earlier, its small lights still shining steadily in the dark. Up past the forest roots and the living soil above them, until we finally reach the thin crust itself, holding every landscape you have ever known. And here we are again, close to the surface, close to where we started. If you think now about everything we passed through to get back here, you might notice something worth carrying with you as this particular journey comes to a close. Nearly everything down there is moving, not quickly, not in any way you could ever hope to watch directly, but moving all the same, continuously, patiently, without needing anyone at the surface to notice or acknowledge any of it in order to keep going. The rock beneath the town you live in, or the city, or the quiet countryside, has been shifting and settling and dissolving and slowly rebuilding itself since long before that town or city existed, and it will keep doing exactly that long after everyone living there now has gone. It isn't moving toward any final destination, nor trying to become anything different. It simply responds to the conditions around it, one small adjustment at a time, across a span of time too long for any single life to properly measure from beginning to end. There is something quietly reassuring in that, if you let yourself sit with it for a moment before drifting off tonight. The ground beneath you is not empty. It never has been. Beneath the soil that holds up your street, beneath the bedrock that anchors the foundations of wherever you happen to be resting right now, an entire hidden world continues its work, indifferent to whether you are aware of it, unconcerned with whatever else might be happening in your life above it, simply continuing, the way water continues finding the lowest path, the way stone continues slowly giving, way to the patient work of rain and root and time. Somewhere tonight, a single drop of water is easing its way through a crack in limestone too narrow to see, continuing a journey that began long before you started watching this video, and that will continue long after you've fallen asleep. Somewhere, a lichen is quietly beginning its slow work on a bare rock face, the very first step towards soil that won't exist in any meaningful sense for centuries yet. Elsewhere, a fungal thread beneath a forest floor is passing a small trace of sugar from one tree to another in a transaction neither tree will ever consciously register. Nearby, magma is cooling by fractions of a degree inside a chamber that has been quietly building pressure for longer than any nearby town has had a name. And far below all of it, hundreds of kilometers beneath the surface, water rests inside solid rock, patient beyond any ordinary meaning of the word, waiting for a slow rise toward the surface that may not complete itself for a length of time longer than anything alive today will ever witness. None of it is waiting for you. None of it needs you to understand it, or admire it, or even remember it once this video ends. It was here before you arrived tonight, and it will still be here, quietly continuing its work, long after you've drifted off and moved on to whatever tomorrow brings. There is a particular kind of peace available in that thought if you let it settle the way water settles into the lowest point of whatever ground it happens to be resting on. You do not need to hold up any part of this. You do not need to keep track of it, or worry over it, or carry it forward in any way at all. It carries itself. It always has. Let your own thoughts settle the same way now. The way sediment settles at the bottom of very still water, drifting downward without any hurry at all, coming to rest somewhere quiet, without needing to arrive at any particular place or conclusion. The ground is still beneath you. Beneath that ground, the soil is still working, and beneath the soil, the roots are still reaching, and beneath the roots, somewhere, water is still dissolving stone by fractions too small to see, and beneath that, deeper than any of us will ever personally travel, rock is still flowing at a pace slower than anything else in this story, quietly carrying the world above, one imperceptible shift at a time, in the same quiet rhythm it has kept since long before tonight began, and will keep long after tonight has quietly become tomorrow. Good night. Sleep well.